Let me begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for the students. Just ask that you to guide our steps today, help the students to ask good questions if they have them. And I just pray that you'd encourage the students each and every day, Lord, to do their best for your glory, Lord. In your name I pray, Lord Jesus. Amen. Let's see here. So, we're graphing rational functions. Do you guys got any questions about anything? There seems to be some confusion in the other section. Maybe it's here too. Like people are like, where are you supposed to turn in the assignment? So like, I know this is like weird, but there's like, you print it out on a piece of paper. You write the answers on the piece of paper and you turn them in class. This is how we're doing it. All right? So it's not electronic. I know it's weird, like you actually have something physical you bring to class and give to a professor. This is like confusing to you guys because you've become so accustomed to doing everything through the computer, right? Like everything's on Canvas until it's not, right?
Was that due today?
It was due today, but I realized that this message did not register with a significant portion of you, so I will take it Friday, okay? If you have it today and you want to turn it in, I'll also take it now so you don't lose it, if you'd like. Anybody? If you did not print it out, but you wrote it out by hand, I will also take that. And I would also point out that this is symptomatic of the fact that, you know, like, you don't have a lot of stuff you're printing out, right? Yeah. Which is kind of sad, you know? You have stuff to print out. I don't know. To me, it's not real unless it's on paper. All this electronic homework, it's all fake.
The having to print it out genuinely did not register in my mind.
Right. Now, again, if you don't have access to a printer for whatever reason, you want to write that by hand, I will take those too. Anybody? All right. So, and just, I will reiterate, you don't have to work out the long divisions for that. You can if you want to. I'm really just interested in seeing that you found the answer to each problem. So if you answer this is the answer for each one, then that's all you had to do. Glancing over it, I see some of you have actually done the long division, which is good for you, right? But that wasn't required. So, everybody top hat? Okay, so I'm going to talk about graphing today. So this is going to take me a minute to write up the instructions here. All right, so hang with me. This is it's going to be about a page of notes here. All right. So we're given f of x in the form, let's say n of x over d of x, where n of x and d of x are polynomials. Okay? So this is a rational function. I'm using n and d this time because I think that might be helpful. Think of n as the numerator, d as the denominator, okay? So the algorithm for graphing this, step number one, is completely factor. Completely factor n of x and d of x, all right? Okay. That's step number one. Step number two is to identify all zeros of n of x and identify all zeros of d of x. All right? And I'm going to make a handout for you guys. In the handout, I'm going to add more notation that would be like a drag for you to write out right now. I'm just going to put it in words here. But I do intend to give this to you as like a handout here sometime in the next week or so. Hopefully Friday. Well, we'll see. Okay, so identify all the zeros of n of x and identify all the zeros of d of x, right? and then put them on a number line. All right, so you make a number line. You know, here's your C1, C2, da da da, whatever. However many you got, you know. However many of these you got. I was trying not to do this, my bad. But anyway, so like you make a number line with all the zeros marked on it, okay? And then, like we always do, with pluses and minuses, right? As appropriate, okay? As appropriate. Add the pluses and minuses. You know, we test the point in each case, blah, blah, blah. Great. Then step 3. Step 3 here. Okay. I want to decide what's the nature of the asymptote for this thing. All right. So step 3 is a little bit complicated. Here I'm going to, well, there's 2 steps to step 3, okay? So if the degree of the numerator is less than the degree of the denominator, then y equals to 0 is the horizontal asymptote for the graph. The lion's share of examples that will ever work in here will be like this. Okay, more often than not, the horizontal asymptote is y equals to 0. Okay, what is interesting is what happens when that's not the case. So if the degree of the numerator is larger than or equal to the degree of the denominator, then do long division. We do long division. And so long division is going to do what for you? It's going to write, well, I'm going to put it in a different color here. The long division, it's going to produce for you f of x excuse me, is equal to p of x plus a remainder term divided by the denominator. Okay. Long division tells you that you can rewrite the rational function as the sum of a polynomial, all right, plus what's called a proper rational function. So this piece right here, this will go to 0 as x goes to plus or minus infinity, all right? So as you look at x getting really large in either the positive or the negative direction, that piece is going to die. I mean, it becomes very small compared to the other piece. And so, in other words here, what we see is that y is approximately just equal to p of x for x going to plus or minus infinity. So p of x describes the asymptotic behavior of the graph. That's what the graph looks like from a million miles away, kind of, sort of. Oftentimes, the polynomial is a very silly, simple thing. It's just a number. So in the case that the degree of the numerator and the degree of the denominator are equal, in that case, the p of x would just be a number. All right? And then you just get a plain old horizontal asymptote. A lot of examples we'll look at are like that. Okay, so obviously, when the degree of the numerator is greater than or equal to the degree of the denominator, we've got some thinking to do there. Okay, so we're going to look at some examples to dive into the details here. Okay, it's not, if you're not comfortable with what I'm saying right now, that's fine. All right, we're going to expand on this in the examples. And then, for you guys, step 4, graph. Now, somehow when I did this last class, I managed to get 5 steps. So I don't know, I got 4 steps for you guys. Last section I had 5 steps. I really wonder how I got 5 steps last class. Oh well. So here, anyway, graphing, a lot of the graphing, it boils down to studying the zeros of the d of x, the denominator and the numerator. Okay, so let's talk about that. So here's the deal. Given, c is a 0 of, n of x or d of x, right? How do we understand the graph? How do we understand the graph? What does that do to the graph? Okay, let's talk about it. So here are the cases. So like case number 1, if x minus c only factor of n of x, then c comma 0 is x-intercept. Very simple. If the factor only appears in the numerator, then that means that that 0 corresponds to just an x-intercept. All right? Number 2. If your factor x minus c is only factor of the denominator, d of x, then what happens? Then x equals to c is a vertical asymptote. It's a vertical asymptote of the graph. So that means that your graph is going to blow up there, like a volcano, or like a one side goes up and one side goes down kind of deal. All right? It's a vertical asymptote, if that's the case. What's the third case then here logically? If x minus c is, it could be in the numerator, it could be in the denominator. What's the other thing that could happen? It could be in both of them, right? And that's where it gets complicated. So this is the tricky part. If x minus c is factor of both n of x and d of x, if it's both in the numerator and the denominator, then there are 3 cases. Okay, there's 3 cases here. Let me do it. So case 1 would be if the order of x minus c is same for n of x and d of x. Sorry, I'll start right. This is no good. So if it's the same, if the order is the same, then c comma the reduced function of c is whole in graph. In other words, if the order of x minus c is equal in the top and the bottom, then what you got a hole in the graph. Where is it? It's at c comma the reduced function of c. I'll explain what the reduced function is in some examples as we go on, okay? If the order of x minus c is larger in the numerator, then c comma 0 is x-intercept, is hole in graph. So the hole in the graph is on the x-axis in this case. So it's like an x-intercept, except it's a hole in that case. All right? And then case 3 is if the order of x minus c is larger in d of x, then x equals to c is vertical asymptote. All right? That's basically the game plan. All right? This is the things we can use to graph a rational function, how to put it all together. All right? Let me actually look at examples, yeah? To try to put some meat on the bones here, so to speak. Let's see here. All right, so example 1. Suppose we have f of x equal to, here we go, x squared minus 4 over x plus 2 times x plus 3 squared. That should do it. We'll start with this. Okay, so first order of business, we need to factor, right? Usually factoring is the first thing you want to do. So factoring here, we get x plus 2 times x minus 2 over x plus 2 times x plus 3 squared. Yeah? Questions? Okay. So we completely factored it. Great. That wasn't too bad because, well, I made it easy for us. Now we're supposed to identify the zeros of the numerator and identify the zeros of the denominator. So if you look at this, right, this is n of x. This is my d of x, right? What are the zeros? What are the zeros? In other words, what makes it 0? I've got a minus 2 and a 2. This one, I've got minus 2 and minus 3. Right? Okay, so that's it. My list of zeros is minus 3, minus 2, and 2. Now we can make a number line. Let's do that. So I've got, let's see here, I said minus 3. Minus 2. 0. 2 would be over here-ish. There's my number line. I've marked all of my critical numbers, right? All of the zeros, either for the numerator or the denominator. Those are called critical numbers. Right? You should recognize we've done this before, right? This is how we solve the rational inequality problem. Remember, if we're going to solve a rational function as like less than 0, we made a sign chart. We listed all the zeros of the top or the bottom, and we tested signs in each case. That's how we solved rational inequalities, or that's how we were going to try to solve rational inequalities. This is the same. It's the same thing again. Okay, so try plugging in a number past 2. How about, think about putting 3 in. What happens? So we would get, 5, 1, 5, 6 squared. Everything's positive, right? So the sum total of it is we've got pluses here, all right? And then we can use the sign flip theorem to propagate those from right to left if you want. So I get to 2, right? Where is this coming from? This is coming from this x minus 2 factor here, right? There's just one of them. What's that? We flip it, right, flip it, exactly. Thank you. Now we get to minus 2. That's coming from the x plus 2 factors, right? How many of those are there? There's 2 of those. So it stay minus. Okay? And then we get to minus 3. Where's that coming from? That's coming from this x plus 3 squared, right? So it stays. Okay? Now, at this point, we've done steps 1 and steps 2, right? We probably should do step 3 before we graph. All right? So I'm gonna work on step 3 now. Wait a minute, is there anything to work on? Oh, there's a hole. That's true. We should figure out where the hole is before we graph, I suppose. Yeah, where's the hole? Let's figure that out. I'm going to write that here. The hole. So we notice that x plus 2 has order 1 in the numerator and the denominator, right? So that's a hole in the graph. Now what's the reduced function here? I didn't really define that for you, but what the reduced function is just when you cancel out the factors that correspond to the hole. So in that case, I'm just canceling out my x plus 2 and x plus 2, and it leaves me x minus 2 over x plus 3 squared. Okay? So the hole is, yes, at, c equals to minus 2, right? Okay, so the f reduced of minus 2, what's that equal to? We've got minus 2 over minus 2 plus 3 quantity squared. What's that? We get minus 4 upstairs, right? Minus 2 plus 3 is 1. 1 squared, still 1. So this is just minus 4. This tells me the hole is at minus 2 comma minus 4. All right, so we want to put that in our graph, all right? Okay, so let me proceed to the graphing. I guess I should stop and say something. What about the y? What about number 3? Is there anything to think about number 3? What happens for this one? The degree of the numerator is what? The degree of the numerator is 2. The degree of the denominator is 3, because you got this first order times the second order. 1 plus 2 is 3. Second over third, that is the easy case. No long division required. We know that eventually the graph goes to 0. The denominator wins in the end. So it's going to tend to 0 long term. All right? So that we have that to look forward to. So there's really not much to say about 3 except that we're looking for y equal to 0 for the long-term behavior. All right, so now let's sort through it. Which one of these is a 0? Which one of these is a hole in the graph? Which one of these is a vertical asymptote, right? We already know, as we've discussed, minus 2 is a hole in the graph, right? How about this? X equals to, so anyway, let's sort through it here. So minus 3, right, is from this x plus 3 squared. That's in the denominator. It's unopposed, right? So that means vertical asymptote right there. We got a vertical asymptote to deal with there. Because x plus 3 is in the denominator. So that means there's division by 0. If we plug in minus 3 into this formula, you get division by 0. When we have division by 0 in the formula unopposed, you get a vertical asymptote. Now if you have division by 0 and you also have multiplication by 0 at the same time, it's complicated. You got to go through the 3 cases. It's either this, this, or this when you have a 0 both upstairs and downstairs. In the case of minus 2, it's a hole in the graph. The hole in the graph is actually at minus 2, 4. So here-ish. Okay? Minus 2, minus 4. There's my hole in the graph. And now how about 2? 2 itself, what's the deal there? 2 is coming from this x minus 2 upstairs, right? The x minus 2 factor is upstairs. There's no other x minus 2 anywhere else. So that is simply a x-intercept. Because if we plug 2 in, we get 0. So that's an x-intercept at 2. All right? And by the way, the thing we learned for polynomial graphing, remember like bouncing or crossing, it's still true here. So if I had if I had something in the numerator that was like squared, it would bounce. If it's the first power, it's going to cross. Of course, the sign chart's also going to tell you that, right? See? It's negative. So what's going on here? Vertical asymptote. So this is something like, let's see here. And then it's positive, right? But the thing is, it goes to 0 eventually. So this has to kind of come back down like that.
How do you know if it goes back?
That's part 3. Y equals to 0 is a horizontal asymptote for this. Yeah.
Isn't there another x changes?
negative, oh, did I miss my minus 2? Oh, minus 2 is a whole.
But there's another point.
Why is there another? This is the minus 2 right here.
Okay, so you don't.
There's no x-intercept. There's no x-intercept at minus 2. Minus 2 is a hole in the graph. And it happens to be at minus 4 for this one. So that's the thing, is you can't just look at the numerator. You can't just look at the denominator. You have to take them both at the same time, because there's a tug of war between them when they share something in common. And that tug of war either works out to a hole in the graph, a hole a hole in the graph somewhere other than the x-axis, a hole in the graph on the x-axis, or a vertical asymptote, which didn't happen here. But this vertical asymptote is just because there's an x plus 3 in the denominator, right? And so this one, it's a volcano down, so it's like one of these deals. All right. So there you go. That is a somewhat ugly version of this graph. I mean, I'm sorry, my graph sometimes, it's probably not lumpy like mine is. If you actually graph it, it's probably more like pretty. But this is qualitatively what the graph looks like, okay? Any questions?
How do you find the hole? Yeah.
So again, the whole is coming from looking at what are the critical numbers for the expression. We have to sort through them one at a time. When we look at minus 2, we study the order of the factors that correspond to minus 2. The 0 of minus 2 corresponds to x plus 2 factors. Since there's one upstairs and there's one downstairs, when this happens, this gives us a hole in the graph. If you have the same number upstairs and downstairs, you get a hole in the graph. Yeah.
If there's like a horizontal asymptote at y equals 0, how come it goes to x?
Because this is y equals 0. I mean, this is y equals 0 is the x-axis, so it's going to the x-axis. It's tending to 0.
I thought with an asymptote it can't like cross.
Well, you can cross through a horizontal asymptote, but that usually happens early on. I mean, this won't happen this is not going to happen in this class, okay? But there are interesting functions like this, for example. Like that. So this function has a horizontal asymptote of whatever this is, 2. And yet the graph crosses that horizontal asymptote infinitely many times. It would be like a spring on a car or something, as it kind of bounces and it gets damped, like a damped spring has something like this. So you can cross horizontal asymptotes as many times as you want. Now, that doesn't usually happen. For our rational functions, the crossings are going to only happen like at the zeros. And like the long term, it's going to do something like this or like this. So you're right, it won't cross the x-axis past our critical numbers. That's by design. The only place where we can cross the x-axis are either the only place we can cross the x-axis is at critical numbers. Sometimes we cross it by literally crossing it. Other times we cross it by having like a vertical asymptote where we kind of flip over. It's like the crossing doesn't always actually go through the x-axis in a sense. Like we have other. Let me just draw the picture. So this can also happen, right? We can get from one side of the x-axis to another by having a graph that looks like this, right? Like that's the only way you can either go through an x-intercept, you go through a hole at the x-axis, or you cross over at a vertical asymptote. That's the only way to get from one side of the x-axis to the other for the graph of a rational function. So, in that sense, you're right. We can't cross the horizontal asymptote past these numbers. But before those numbers, you can cross the x-axis if you have, like, for example, this one, this x minus 2 makes us go through 0 there. Okay? So, if we wanted to improve our graph, what would this point right here be, guys? Can you tell me? The y-intercept. Yeah, what's the y-intercept here? F of what? How do you find the y-intercept? F of 0. What is 0 here? Plug in 0 into the formula, right? minus 4 over 2 times 9. So the y-intercept is actually at minus 2/9, right? Which shows you how incredibly bad my graph is, right? Because I've got the y-intercept like where? Yeah, it's kind of like at -2-ish. So it's actually the graph. If I improve my graph with this new insight, right? If I want to fix it, it looks more like it's more like up here, right? So this graph is more. It's more like that-ish probably. But anyway. Okay, so anyway, you can always add points to, try to do better. And if you have graph paper, of course, you can do better. And this is definitely not something that's going on in here. It's smooth. The graph should be more smooth. But anyway, how many of you guys had art class in high school? Some of you did. So I should have like a little question at the start of the graphing problem. Had art class in high school versus not had art, and I should grade you guys by different scales, right? If you had art class in high school, I should hold you to a much higher standard for the smoothness of your curves and stuff, right? No? 50% of the grade is the smoothness of the curve. See, if you were smart, then you'd always just be like, the graph is a line. I draw my y-axis, I draw my x-axis, I draw a line. I have drawn it perfectly smoothly. I brought a ruler to the test, right? You have to give me 50% of the credit. And you don't have to think at all, right? Just every graphing problem, you just be like, line, 50% of the credit, I'm done. Ha-ha, no studying for me, right? Some of you, this is sounding like a really good idea, isn't it? Yeah. This is why we cannot have nice things in here. Let's see here. All right, let's move on. Okay. How about example 2? Suppose we want to graph y equals f of x equal to, here we haven't done this one in a while, x cubed plus 3x squared plus 3x plus 1 divided by x squared plus 4x plus 3. Let's graph. Oh, okay, that's slightly uglier than I want. So let's tack on oh, that's going to make it worse. My bad. I better put something down here. Oh, I don't know. X minus 3. There you go. So this is kind of a tough problem, but it's not impossible. Okay, let's sort through it. How do you factor that top thing? Do you guys know? So this is right on the edge of being a reasonable factoring question. So if you look at the perfect cube formula, right? Remember how that works? On your formula sheet, you've got a cubed plus b cubed equals a plus b times a squared. Oh no, that's not it.
Wouldn't it be grouping since there's 4 times?
Goodness gracious. Yeah, you're right. That would be how we think about it in here. See? Oh man, it's finally caught up with me. So something that's missing from the presentation yet for you guys is Pascal's triangle. So I'll show you. This is Pascal's triangle. So the next line goes like this. 1, 4, 6, 4, 1. Okay? And what this tells me is how to FOIL out things. For example, a plus b quantity squared. I do a squared plus 2ab plus b squared. That 2, right, I can think of as coming from that 2. If I do a plus b cubed, Pascal's triangle tells me that I do a cubed plus 3a squared b plus 3ab squared plus b cubed. And this 3, I can think of as that 3, and this 3 is that 3. If I want a plus b to the 4th power, I've got a to the 4th plus 4 a cubed b plus 6 a squared b squared plus 4 ab cubed plus b to the 4th. So the way the pattern is here is the power of a decreases as you go across by 1 each term, and the power of b increases by 1 as you go across each term. There's a complete symmetry between the way a and b appears in the formula. Anyway, this is Pascal's triangle. So obviously, that is like way, way faster than multiplying this out, right? We'd be here all day like multiplying this out term by term, right? This is a super nice trick to know about. My point to you is simply that this right here, if you look at it, you can recognize that that's exactly, and so I'm sorry, I really shouldn't have asked you guys this problem because I don't think we have Pascal's triangle in any of the homework. I meant to put it back in the homework and I never did, so I'm depriving you guys of that. This is not on the test. Like, this is not on the test. This would be bonus if it was. Okay? We have not covered it in the tested homework part of the course. Okay, anyway, so this is actually x plus 1 cubed, though, is my point. All right. Okay, so how about, in contrast, the denominator you can factor, right? Can you? You can factor that, right? What's this? This is what? I'll leave the x minus 3 there, no need to mess with that. How about the plus 1 and plus 3? Yeah. Aha. Okay, so great. We've got it. We draw a number line. Here's our f of x. What are my critical numbers? My critical numbers are minus 3 and 3 and like a minus 1 right there, right? So the critical numbers are minus 1, minus 3, and also 3. Yeah? Test some points. I think if we plug in a number like 4, it's going to be positive. So I start out pluses. Now do I flip the sign or keep it at 3? Flip or stay? What's that? Flip, because we've just got one copy, so we flip. How about minus 1? Now there, you have 3 x plus 1s in the numerator, and you have 1 x plus 1 in the denominator. That's a total of 4. Stay. Stay minus.
That would be about.
Yeah. Yeah, I think it actually will be a bounce. Yeah, in a sense. And then at minus 3, again, we just have the x plus 3, so we flip again. Okay? Now, oh no, look at that. Well, well, I'm sorry, I'm debating here. There are different ways to go about doing step 3 here because we were able to factor that. Like, we could dodge the long division and just like simplify here. I need to address it, right? Like, step 3 is non-trivial for this one because we have order 3 and order 3. So there is going to be it's not y equal to 0 for the horizontal asymptote, it's something else. All right? So let's say this. This is equal to, what is this equal to? This is equal to x plus 1 squared over, x squared plus 4x oh, excuse me, x, my bad, over x plus 3 times x minus 3, right? For what? X not equal to what? Minus 1, right? For x not equal to minus 1, that's the formula. Okay? So for step 3, I'm really interested in how the formula works for really large values of x. So it makes sense to study that for the long division. So here we have x squared plus 2x plus 1 divided by x squared minus 9, right? And so I can do long division there. And you know, the truth be told is you don't really need to do the long division here. If you really understand what's going on after you do a bunch of these, you'll already know that the horizontal asymptote is just going to be the ratio of the leading coefficients of the polynomials which we're dividing. So like we're going to get 1 here. Of course, the reason for that is I put a 1, and that gives me x squared plus 2x plus 1. I subtract, I get, you know, minus 2x minus 10. So what I have in purple right above, it's equal to 1 minus 2x plus 10 over x squared minus 9. That is the behavior of our function. That tells us how the function behaves for large x. Yeah? Like I can see from that, oh, this function's going to 1 for large values. Okay? So that partly informs my graph. All right, where's 0 in all this? So about right here, right? So let's graph this thing. Let's see, do we have any vertical asymptotes? I think we do, right? Because plus 3 and minus 3, they're unopposed, right? So we got vertical asymptote here and here. Okay. How about minus 1? What's going on at minus 1? So this tells me y equals 1 is horizontal asymptote. Okay, so that's roughly speaking here-ish. So what did you say? What do you think about minus 1? What's the deal there? There's that tug of war I was talking about. There's some in the numerator, there's some in the denominator. Which case are we in? Order of the numerator has 3. Order of x plus 1 in the denominator is 1. So if we believe my algorithm, we're in the case that the order of the numerator is larger, which means that c comma 0 is a hole in the graph. So we actually have minus 1 comma 0 is a hole in the graph. All right? Right there. Now what goes on? So yes, somebody said a while ago it bounces there. You're right, but it bounces off the hole in some sense, right? So like what's going on here is it's got to look something like this. Bounce like that. See, I have to obey the signs up here. It's all negative, right? It stays negative. I'm never happy with my pictures here.
So why is there a hole there?
Because at minus 1, we have like this.
Oh.
See, what you have is x plus 1 cubed over x plus 1. And if you just do that, it leaves you with a total of x plus 1 squared, which is going to be 0 when you plug in minus 1, right? Technically speaking, that's not in the domain of the function, though, because it is still true. You can't actually plug minus 1 into the original formula for the function because you have division by 0. Multiplying by 0 doesn't make that better. It just means that the graph has a particular pattern that we can understand. So that's that part. And how about over here? Well, it's positive over here, right? So it does something kind of like this. All right? And it's getting drawn into this y equals 1 asymptotically, okay? And let's see what else here. Then we're positive over here, right? And then we kind of just drift into that y equals 1 long term. That's the horizontal asymptote. So there you go. If you want to improve my graph, we could figure out what is f of 0 again. What would that be? F of 0 is going to be minus 1/9. So as you can see, I have again chose poorly. Like it's really more like up here. If I was smarter, I would have. As a general point of order, if you graph by making a dotted line first, and then you like connect the dots in your dotted line, that tends to make better looking curves.
Could you explain the y equals 1 again? I didn't understand.
Y equals 1?
Yeah, like the horizontal asymptote.
So I was looking at what does this formula look like? What does this formula give when you rewrite it in terms of a polynomial plus a proper rational function? So if I follow my 3 exactly, just to answer your question without redoing it, it's because we found that when x is not equal to 1, this is a formula for the function, which means it's going to go to 1 eventually. Listen, there's another way to look at this. And when I write out the handout for you guys, another way you could look at this is this. So for this one, we have y equals to x cubed plus 3x squared plus 3x plus 1, right? And if you multiply out the denominator, what do you have? What is x squared plus 4x plus 3 times x minus 3? What's that give you? X cubed plus 4x squared plus 3x squared minus 12x minus 9, also known as x cubed plus x squared minus 9x minus 9. So I've got x cubed plus x squared minus 9x minus 9. All right. If that's your formula, whenever you have something like this, just as a rule of thumb, the way to graph something like this, it's always going to be like all you have to do is look at the leading coefficients of the highest powers, and that will give you your horizontal asymptote.
Okay.
Like hypothetical, if we were graphing y equals, x to the 6th plus x minus 9 over 3x to the 6th plus x plus 42. I wouldn't do this because we can't, this would be an unfair question, because for us to do it like we're doing today, what would we have to do? Step number 1, completely factor the numerator and the denominator. Do you want to do that? I don't want to do that for this problem, but what I can tell you from this is that the horizontal asymptote for this graph is 1/3. That I can.
So that's like always?
If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the ratio of the leading coefficients, yeah. That's the result of the long division. Anyway, listen, this is the tricky part, all right? So I will try to do more easy examples next class. If you look at the course schedule, we're ahead, right? Because this is what I cover. This is essentially the material we cover right before quiz 2. So we're just going to keep doing more and more examples of this. There really isn't, I don't think, much more new material to quiz 2. This is what you need to understand to succeed in quiz 2. So thanks, guys.